evaluation of definite integral by substitution. So we have seen some aspect of this, but there is another aspect to this which I have not shown. So let me discuss that. So the first methodology is something that you guys have exposed to. So what is it? We make the substitution, we integrate it, we resubstitute the original variable back, and then we evaluate the resubstituted expression. So for example, so here I'm going to start off with calling t as x squared plus 1. That's very obvious for you guys. So dt by 2 would be x dx. Then generally I'll start off with taking the indefinite integral. In terms of representation, you know me, I would like to represent it very well. So we have this x dx. Then we have this. Then f of t would be 1 by 2 dt by t. Then f of t is equal to 1 by 2 log, not lot, log t plus a constant. So when I resubstitute back, therefore f of x is equal to half log of x squared plus 1. Yes, I know that most of you would have been able to tell this directly. I agree. This is just an example. And by the way, we have to substitute the limits also. Therefore, integration of 3 to 4. F of x would be f of x 3 to 4, right? This is nothing but your f of 3 minus f of 4. I'll write it here itself. F of 3, f of 4 minus f of 3. So this would be 1 by 2 log of, so this would be how much guys? 16, 17, 17 by 10. Plus, oh, there is no constant. So the reason that you should be knowing by now, 17. Okay, anyways, that's our answer. So this is traditionally what we did. So let me show the program aspect of it. Let's have a perspective, different perspective now. So we have x by x squared plus 1, 3 to 4. Right, those are your limits and everything. So that's your graph, 3 to 4. And the approximate answer is 0.265. Sorry, it's 0.266 approximately, 3 decimal places. Now, we can do the same thing, actually the same set of calculation and everything, right? We'll make the substitution, calculate the new limits. This is a new thing. What does that mean? So in this example, we had from 3 to 4 and we had x dx by x squared plus 1. So substitution and all of that we do, right? Same set of calculation, but here when we tell let t be equal to x squared plus 1, how we calculate dt, right? So dt we calculate on a same line. We'll tell for x is equal to 3, t is equal to 10. For x is equal to 4, t is equal to 17. That's it, as simple as that. And so your f of t will start looking like 10 to 17, right? 3 to 4, 10 to 17. Then this would be 1 by 2, 1 by 2 dt by t. So it's kind of commonsensical if you think of it mathematically, right? Because end of it we get the same numbers. So 1 by 2 log of t from 10 to 17. So this would be 1 by 2 log of 17 by 10. We don't need modulus technically. So 17 by 10, same thing. Can you see that? So I didn't write modulus over here, reason being it's positive. Now I'm curious about this actually. When I was doing it, I was curious about it. So 17 to 10, right? And the function is 1 by t and all of that. So, oh sorry, 1 by 2t. That's what I was thinking. You can see that here too it is 0.266. 0. Same number. I'm just changing. Can you see that? This is x by x square plus 1. That's the expression and this is your answer. When I press the other one, which is 1 by 2t, 17 to 10, we have the same number and these are your graphs. So that's the first graph. This is the second one. Right? It's not moving. Okay, now it's moving. Right, guys? Right? That's how we get to do this with substitution. Both are correct. Whatever is comfortable, you guys, you can do that. Actually, this is very comfortable. Or only thing that we did was substitution over here and simplification. By chance, substitution and simplification looks tough, then just ignore it. Do your integration, go back to the original expression and substitute. That's it. Okay? Yeah. Just remove this over there. So 1 by 2 and all of that. So I just wanted to make a point. I had just 1 by t at the start. There was a 2 missing, so I had to put that. Right? The expression tells it to be so. Here too you can see that. Okay, you can pause and copy everything.